Hi, and welcome back to Unit 4.0. This is part 2 of 2. So in this section, what we're going to look at now is doing some of the calculations that are associated with gases. We're going to look at the behavior of gases using what's called the ultimate combined gas law and also the ideal gas law. So there's going to be some calculations that we're going to be doing here, but we're also going to predict behavior of gases just based on things that we know about gases and using those equations. So before we begin, I just want to go into the gas laws that you're going to be looking at. This is called the combined gas law. I call it the ultimate combined gas law only because I've included the N, which means moles of gas. You, for a while now, have been looking at the mole map and see the PV equals nRT equation. So N in that equation stands for moles. In the combined gas law, it's saying that, and this gas law is useful when you're changing a property of gas, whether pressure, volume, temperature, or moles. Your initial pressure volume divided by your initial moles and temperature is equal to your final pressure and volume divided by your final moles and final temperature. And so you can use this when you're changing, again, one of the properties. So in a case where you're not looking at a change, where like everything is basically staying the same and you want to just calculate the pressure, volume, moles, or temperature at a given time, this is where you're going to use the PV equals nRT equation. P is for pressure, and that must be in atmosphere. V is for volume, and it must be in liters. N is for moles. R is the gas constant, and this is what locks the other terms into their units. So as you can see here, the gas constant unit has liters, atmosphere divided by Kelvin mole, and so that's why the pressure, volume, and moles all must match those units that are shown here. And then, of course, temperature must match the Kelvin unit showed in the gas law. The gas constant, 0.0821, is one that you eventually will start to memorize. You don't have to memorize it for now because it's usually provided for you. All right, so behavior of gases are predictable. And that's one of the cool things about gases and why chemists like to study them. So you can predict the change in the pressure, volume, moles, and temperature by knowing a change in another property. And you can also quantify that change as well. You would need to know, of course, one thing is important to know the type of container. And there are two types of containers that you need to know in order to make these predictions. The first type is rigid. That's one that cannot expand or contract. And an example of that would be a tank. The other is non-rigid or flexible container. And that means it can expand or contract. And the important thing about a non-rigid container is that the external pressure is equal to the internal pressure. It maintains a balance in pressure. Examples of non-rigid containers are balloons or pistons. So in both cases, you can expand or contract it, and it will expand or contract in order so that the external pressure is equal to the internal pressure, sort of like an equilibrium. Okay, so let's see if we can predict the behavior of gases qualitatively, saying whether it increases or decreases when you heat up a container A, which is rigid, and B, which is non-rigid. So start with the number of moles of gas. Do they increase, decrease, or stay the same if you heat up a sample of gas? Great, they will both stay the same because you're not adding or removing gases in any case. If it's a closed container, a sealed off container, it will stay the same. How about volume? What happens to the volume when you heat up a container? So for a rigid container, the volume can't change, so it must stay the same. But for a flexible container, if you heat up the gas, the container, the piston will sort of go up. And so as you can see here, the volume has expanded. And so the volume here will increase. What about pressure? What happens if you heat up a gas in a tank or a piston? So in the tank, the pressure is going to build up because remember the particles are now moving much faster and they're hitting the walls with more force. So the pressure inside the tank is going to increase. That's the reason why it's important to make sure if you have a gas tank that you don't expose it to extreme heat or you're going to have an explosion. The piston, on the other hand, what happens is because the volume increases, it sort of equilibrates. And so the pressure is the same as you started off with. The pressure on the internal pressure is going to equal to the external pressure, and the volume helped to take care of that. So the pressure actually doesn't change here. You sort of release the pressure when the volume expanded. Last, what about the temperature? Of course, so since you're heating it up, in both cases, the temperature will increase. All right, so you can sort of just predict that based on what would happen qualitatively based on just your experience. You can also use the combined gas law to make those predictions. So I just want to go through this with you. For the combined gas law, you're not locked into units as much as you are locked in with the ideal gas law. So there are different units and they're shown here. The main thing is with your units, they must be consistent. The only unit that has to be in a certain value is temperature. That must be in Kelvin, but everything else, as long as the units are consistent, like pressure can be in torr, millimeter mercury, or Pascal. Volume can be in liters or milliliters, again, as long as it's consistent. And of course, N stands for moles, so moles is pretty much in moles, or it could be millimoles or whatever. All right, so we're going to predict the behavior of a gas quantitatively now using the combined gas law equations. So they're giving us a 12-liter propane tank filled with 2.2 kilograms of propane. Initially at 25 degrees Celsius is heated to 78 degrees Celsius. What is the pressure inside the tank if the initial pressure is 102 atmospheres? Okay, so the first thing is we don't need everything in this equation. We only want to focus on things that change. So we're going to cross out anything that is constant or is not included in the problem. So if we look at our problem here, the volume of the tank does not change. So I'm going to cross that out. It still is a rigid tank, so the volume is not going to change. I'm also going to cross out the moles because I'm not adding or removing moles of gas. So I'm going to cross the moles out. So the only thing that's really changing here is the temperature changing, and that's going to impact the pressure. The temperature changing, so that's going to impact the pressure. So what I'm left with is P1 over T1 equals P2 over T2. And basically all I've got to do at this point is just plug it in and just make sure my temperature is in Kelvin. So my P1 is 102 atmosphere. P2 is what I'm trying to find. T1 is in Kelvin is 298 K and T2 is 351 K. And so I go ahead and just plug that in, cross multiply and solve, and I get P2 is 120 atmospheres. So what I want you to do now is I kind of went through this problem quickly. You're going to pause this video and you're going to use sort of reading strategies or whatever you need to use to figure out how did I go from one step to the next. If you need to play the video back, feel free to do so. And make sure you're taking notes as you're doing this. Okay, so let's go on to predicting behavior of gas quantitatively, this time using a piston, so not a rigid container. So in this case, we have a 12-liter frictionless piston filled with 2.2 kilograms of propane, initially at 25 degrees Celsius and 1 atmosphere, and it's heated to 78 degrees. What is the final volume of the piston? So what are we focusing on here? That's what we need to figure out. We want to know the final volume, so that means that I want to keep my V's. And they're telling me that it's heated from 25 degrees Celsius to 78 degrees Celsius, so that I know that my temperature is going to change. So V and T seem to be important. Am I removing any gas or adding any gas? No, so that means that my moles are going to stay the same, so I can cross those out. And then also, since this is a expandable container, the pressure is also going to be constant. So remember, we're going to cross out pressure because that doesn't change since it's an expandable container. And moles we're going to cross out because that doesn't change. Leaving us with this equation. Now what I want you to do is I want you to pause and fill in your values for V1, V2, T1, and T2. One of them will be your unknown. Great, once you have that all filled in, then you can go ahead and cross multiply and solve, and you get your V2. Okay, so now let's predict what happens when you remove gas from container A or B. So now we're actually removing, as you can see, here's sort of like a leak. So what happens to the moles? In both cases, it will decrease if you remove gas because you have fewer gas. What about the volume? For A, it will stay the same because it's a rigid container, so the volume doesn't change. But for B, if you remove gas, the piston is going to go down. And so that means the volume is going to decrease. For A, the pressure is going to decrease because you have fewer moles of gas, so they don't hit the walls of the container as often. Here, the pressure is going to stay the same because that's one of the good things about piston. The pressure on the inside is going to equal the pressure on the outside. It will equilibrate itself. Finally, the temperature. We didn't do anything to the temperature, so that will remain the same. Okay, now I want you guys to try this CFU. So you're going to pause the video and you're going to read through it and see if you can figure it out. Okay, so here is the answer. You are going to cross out any variables that are not constant. In this case, that are constant, volume and temperature stay the same. That doesn't change. So we're just looking at pressure in moles. So what we need to do is we need to calculate our moles and plug them in along with the pressure. I calculate mole using mass over molar mass for each thing. And then I plug it into the equation and I solve for pressure. Take a moment to look over my work. And if you have any questions, write them down. Okay, CFU 9. You're going to try this one now. So take a moment, identify the variables that are changing, what stays the same. And when you press play again, the work will be revealed. Okay, so we're going to cross out anything that is constant or not included. In this case, volume and temperature. The volume stays the same. It should have been pressure that's crossed out. So you want to cross out the pressure, not the volume. Keep those. And the moles. So you can go ahead and plug in your moles and your volume, and then use that information to solve. Okay, we have a couple more CFUs. For this next CFU, CFU 10, I want you to read it carefully, and you're going to annotate like with information that you have. And when you press play again, the work will be shown. Okay, so cross out any variables that are constant. In this case, moles and temperature stay the same. So we just left with pressure and volume. We plug in our information there, and we get the pressure. So if you're looking at this stuff and you're like, I'm really confused, I'm not sure where you're getting it from, your job is to pause the video and to go back and make sure you can see like, oh, where does she get V1 is equal to 80 milliliters, etc. So that's sort of what you have to do as an active learner in this. All right, couple more CFUs. For the next set of CFUs, I want to remind you all about the initial equations that we have. We had two sets. We've been using this one, but there's also this one here as well. And we use this one when things do not change. So let's go back to so in this CFU, you're going to read through it and see if you can identify the key information. All right, I'm going to give you a hint for this one. So the hint being that in here, nothing is changing. So we're not going to use the combined gas law, but the ideal gas law, PV equals nRT. And I've already identified your pressure, your volume, your N, and your T. R is the gas constant. So you can go back in your notes and you can find that value. And then this just becomes a plug and chug problem. Pause the video now and see if you can solve it. All right, so here's the work for that. We're solving for moles, which is what we're looking for. And then this is my work. So take a look this over, see if you can figure out how I got this. All right, last CFU. Again, you're going to pause it and read it. Okay, here's my hint. For this one, things are changing, so you do want to use the combined gas law. And I've already identified things in the combined gas law. So pause the video now and see if you can solve. Okay, so we're using P1 times D1 equals over T1 is equals P2 times V2 over T2. This image sort of got messed